Hi everyone, and welcome back to our YouTube channel. In this lecture, I will give you the definition of basic column and non-basic column, and I will also show how to find the basic columns as well as the non-basic columns. And following that, in the end, I will show you also an important property that we will be using when we want to solve homogeneous systems related to basic columns. Okay, now let's start with the simple definition of what a basic column is and then what a non-basic column is, and then try to find the basic columns of a given matrix. Okay, and here's the definition. Okay, here is the definition. And the basic columns actually are the columns that consist of pivot elements or the pivotal positions. So in other words, the columns that consist of pivot elements are said to be basic columns. And the remaining columns besides the basic ones are called the non-basic columns. So in other words, we have two kind of new definition of columns, which are basic or non-basic. And how do we find these columns? Let's first start with the simple explanation and then give a simple example to see how we can do that. Okay, and the way to do so, in other words, in order to find the basic columns of a given arbitrary matrix of size n by n, we need to first reduce our matrix given to either row echelon form, and in short REF in capital letters, which means row echelon form, or reduced row echelon form. Here is the first step we should take to find the basic columns of a given matrix. So we are given the matrix, and then by simply performing elementary row operations as usual, we reduce our matrix into that of either a reduced echelon form or row echelon form. And to do so, we either use Gaussian elimination method and Gauss-Jordan method. And again, it doesn't matter which technique we use, we will find the same basic columns. So you can use your favorite one. You can either use Gaussian elimination method, where we reduce our matrix to row echelon form, or Gauss-Jordan elimination method, where we convert our matrix into that of a reduced row echelon form. Okay, suppose now I choose to use Gauss-Jordan method, and let's first convert our matrix into reduced row echelon form. And as you notice, the matrix given in the first place is not in the reduced row echelon form. Why? Why is that? If we simply remember the definition of what a reduced row echelon form is, first of all, it needs to be in the row echelon form. In other words, we need to have a strictly increasing number of zeros starting from the top most row to the bottom row, right? So you see there is no zero values here, so we need to arrange them first of all. And the second thing, then, in each non-zero row, the leading entries should be equal to 1, and the values both below and above these pivot elements should be equal to 0. And then we will have a reduced row echelon form. And if we use this elimination method, then it means that we are using the Gauss-Jordan elimination technique, right? So, and after we have this reduced row echelon form, to find the basic columns, we simply examine which columns have the pivotal positions, or in other words, the pivot elements, and the columns that have the pivot elements after we are done with this elimination process with this Gauss-Jordan method, then we produce these columns as the basic ones, and the remaining columns are also called the non-basic columns. Alright then, we know what we should do, and we know the steps that we need to take in order to produce the desired output. Alright then, let's start and convert this matrix into the reduced row echelon form, and in the very first place it is not in that form. Okay, start with elimination process. Suppose I apply Gauss-Jordan technique, so I need to replace both row 2 and row 3 by something else to eliminate the first values in each of these rows. So then what should I do? I add row 2 minus 2 times row 1, and for the row 3 I sum row 3 with 2 times row 1 in order to eliminate the very first values in the second row and the third row. 2 and minus 2 should be 0, right? So our new matrix becomes what? Let's see what it becomes. Right? See, I have not done anything with the first row yet, so just write the values here as they are. But for the second row, so minus 2 times r1 plus r2, alright? So this is equal to 0, right? And this is 3, and this is minus 7, and this is 0, because minus 2 times 1 minus 10 plus 2 is equal to 0, and this is minus 5. And for the third row, okay, here is 0, and here is 1, here is 5, and here is 1, and here is 7. Alright then, as you notice, we're done with the first row and with the first column as well, because the leading entry in the first non-zero row, which is row number 1, is 1. So this is one of the restrictions that we need to satisfy to apply the Gauss-Jordan method, and we eliminate all the values below the first pivot element, so they are now 0. Okay, let's jump into the second row, which is and I look at the second row. As you see, it is a non-zero row as well, but the leading entry is 3. So what should I do? First of all, I need to again perform a elementary row operation to turn this value 3 into 1. So I replace row number 2 by 1 over 3 times r2, so which will yield us a new matrix as desired. Let's see. So I got 1 minus 1, 2, 1, and 3. And in the second row I got 0, 1, minus 7 over 3, and 0, because 0 divided by 3 is again 0, and minus 5 over 3, and the third row remains unchanged, so I just put the values of the third row as they are. Oh, sorry, this is 0, right? And well, let me do it clearly. Okay, this is 0, this is 1, 5, 1, and 7. Now what I get? Okay, the pivot element in the second row is now 1, but what should I do is I need to eliminate both the values below the pivot element and above the pivot element. So this should be 0, and this should be also 0, right? And then how can I do that? Again, I continue to perform elementary row operations, and now I need to replace row 1. Okay, I need to replace row 1 plus row 2. That's sufficient for us. And for row 3, I need to replace row 3 by row 3 plus, and again I of course apply an element wise addition, right? So I add this terms in the rows element by element, term by term. So R3 plus minus 1 R2. Okay, now our new matrix becomes, let's see what it becomes. I just added first and second row together. So in the first row now I have 1 0, and of course 2 minus 7 over 3, right? We of course perform the arithmetic operations, we just make the computation. Okay, equalize the denominator, and it is nothing but minus 1 over 3, right? Because 3 times 2 is equal to 6. 6 minus 7 is minus 1. So minus 1 over 3. This is 1. And 3 minus 5 over 3. And again the same. The denominator is 3 here. So I put the denominator. Hidden denominator is 1, 9. 3 times 3, 9. Minus 5, it's nothing but 4 over 3. So now we have 4 over 3 here. Okay, and in the second row we have not done anything. We have not done anything here in the second row at this step. So I just put the values as they are. Okay, minus 5 over 3. Okay, and for the last row I just subtract R3 from R2, so what I obtain is 0 0, and then don't forget 5 minus minus 7 over 3. So with respect to the rule of subtraction in the rational numbers, this becomes plus, and it is 12 over 3, which is equal to 4, right? So this is 4, and this is 1 again, and last arithmetic operation, 7 plus, it becomes 7 plus 5 over 3 as earlier, and again, so it is 26 over 3, right? 26 over 3. This is what we obtained. Now I check out to see whether or not I'm done with the elimination process. You see, in the first, I'm done with the first row and second row, because the first pivot element is 1 in the first row, and below the first pivot elements all values are eliminated, and the second pivot element was 1 in the second row, the non-zero, the first non-zero element, the leading entry, and below and above we have only zeros, so we are done with it as well. The only thing left behind to complete the Gauss-Jordan elimination method is that now we have the next pivot element, right, which is 4 in the third row. So you see, we have 4 here. So what should I do? Well, I need to convert this value to 1. And how can I do that? I replace row 3 by 1 over 4 row 3. So now I get 1 0 minus 1 over 3, 1 and 4 over 3. And 0, 1 minus 7 over 3, 0 and again minus 5 over 3. And for the last row we got 0, 0, 1, 1 over 4, and we got what? 26 over 12, right? 4 times 26 over 12. So we got 26 over 3 divided by 1/4. So when we turn it upside down, we got here, and canceling with 2, which we have 13 over 6. Okay, 13 over 6. All right then. And again, I check to see whether or not I reach to the final desired result, and see almost we are there, but there is one more step to be taken in order to finish this Gauss-Jordan elimination method, because here is the last pivot element, but above the last pivot elements we have minus 1 over 3 and minus 7 over 3, and these values should be eliminated, right? So again, I will perform one more elimination process, one more elementary row operation, where I replace R1 by R1 plus 1/3 R3, and again for the second row I replace row 2 by row 2 plus this time 7 over 3 times R3. So now what we get? Let's see whether or not we reach to the desired result. Okay, and there is no change in the last row, so I just put the values of the last row right over here without changing them at all, so they're all the same. Okay, and what is changed is the first row as well as the second row. Okay, so R1 plus 1 over 3 R3, so we got here 1, 0, 0, and we got 1 over 12 here, adding it to 1, we got 13 over 12, and again if you multiply this, yes, we got 13 over 18, and if we sum them up with 4 over 3 and equalize the denominators, then we got 24 here, 13 here, 37 over 18, 37 over 18. And for the second row, again R2 plus 7 over 3 R3, we got 0 here, we got 1 here, we got 0 here again, and 7 over 12 here. And for the last entry of the second row, we got what? So we multiply, you see, 7 over 3 times 13 over 6. So here we got 91 over 18, and we added to minus 5 over 3, right? So which means we subtract actually. Okay, and again equalizing the denominator, you see we got 61 over 18. So there it comes, 61 over 18. Alright, now let's see what we get, what we have found. Am I done with the Gauss-Jordan elimination process? Okay, I check out to see row by row, and this is the first pivot element, this is the second, and this is the third pivot element. And first of all, now our final matrix is in the row echelon form. We have a strictly increasing number of zeros right over here, and below and above each pivot element we have zeros, and each pivot element is equal to 1. So we are done with Gauss-Jordan method, and we found the final matrix, which is in the reduced row echelon form, right? So this matrix is now in reduced row echelon form. That's great. That's good news for us. That's because, you know, how do we find basic columns or non-basic columns? If you remember, the basic columns are nothing but the columns which consist of pivotal positions or the pivot elements. And to find them, we need to reduce our matrix into either a row echelon form or reduced row echelon form, and find what the pivotal positions are, and then the columns that include that pivot elements are called the basic columns, and the remaining ones are called also non-basic columns. Okay, all right then. Now, what are the basic columns with respect to the final matrix? All right, as you see, the pivot positions is in the first row, second row, and third row. Let's use another color. Let's mark them with black. So this is the very first pivot position. This is the second one, and this is the third one. And all right then, so our basic columns, we know the definition of a basic column, and the basic columns are the ones who include these pivot elements. In other words, our basic columns are, with respect to the obtained matrix, the first column, right, which includes the entries 1 0 and 1 0 0 from top to bottom, right? This is the first basic column I circled in black for you, and this is the second basic column, which includes the second pivot element, right? So 0 1 and 0, and the third basic column is that 0 0 and 1, right? The third column. So these are the basic columns. And why is that? Because they consist of the pivot elements. So these are the basic columns. Alright. And how about the non-basic ones? And the remaining two columns are non-basic columns. So in other words, fourth column, right, and the fifth column are the non-basic columns. And if you represent them by this vector 13 over 12, 7 over 12, and 1 over half, the fourth column and the fifth column are the non-basic columns. So which is actually 37 over 18, 61 over 18, and 13 over 6, right? This is the fifth column, and these two columns are the non-basic ones. Okay, and these are the non-basic columns. And why is that? Because they don't include the pivot elements or the pivotal positions. So these are the non-basic columns. So we now obtained basic columns and non-basic columns, and we know how to find them, right? The basic procedure works as the following. We first convert our matrix, the given matrix, into either reduced echelon form or row echelon form by either applying Gaussian elimination method or Gauss-Jordan method, depending on our choice. And then after obtaining the desired form of matrix, then we check to see where the pivot elements are. In which columns do we have pivot elements? And the columns that include those pivot elements are called the basic columns, and we extract them from that matrix. And the remaining columns are called the non-basic columns, which are the columns actually that they do not include the pivot elements. And one important property, as I mentioned in the very early in this lecture, there's a key observation that we need to make between the basic columns and non-basic columns, and here's that observation. So we have non-basic columns, and a good property says that non-basic columns can be written or expressed in terms of some combination of basic columns. And what I mean is this: for instance, our non-basic column, one of our non-basic columns, actually 13/12, let's write it in this manner to save space, 7/12, alright, and 1/2. So is it possible to write this non-basic column in terms of some combinations or some summation, you know, an algebraic sum? I'm trying to express this vector as an algebraic sum of the basic columns, and if it is possible, then I will show. Okay, how can I do this? So in other words, I will use this basic columns plus second basic column plus third basic column, which is 0, 0, 1, right, from top to bottom. All right, and as you might notice, well, it is really possible. That's because if we select the coefficients of these basic columns, such as this, for instance, 13/12, and this one is 7/12, and this one is 1/4, then what we have here? So this means that yes, we are able to express our non-basic column. I selected the fourth one. I can also write the fifth one as well. So we express the non-basic column as an algebraic sum of the basic columns, which is actually called a linear combination. And these are the coefficients, and these are the coefficients, right? These are the coefficients of the basic columns. So, which means that, for instance, if multiplying by a scalar means we multiply each term or each entry of the matrix or vector by that value. So multiplying by 13/12, the first we got 13/12, 0, 0, right? Because multiplying by 0 gives us a 0 value back, so no change. Let's raise this, it's too much, right? Yep, let's do it. And multiplying by 7/12, we got 0, 7/12, and 0. And multiplying by 1/4, we got, so I multiply 1/4 by all entries, you see. 1/4 times 0 is equal to 0, so I put 0 values here. So the first two values are 0, and 1/4 times 1 is 1, 1/4, right? So now we have this, and if I sum them up, I perform the element-wise summation. So I sum this value 13/12 with this and this in the same order. So I got 13/12 for the first spot, and I sum this value this value and this value together for finding the second entry, right? So what I got 7 over 12, because 7 over 12 summed with zeros is equal to 7 over 12, and for the last entry I got 1 over 4 as desired. So as you see, we are on the right track. So we are able to write the non-basic column in terms of basic columns. In other words, we express a non-basic column as an algebraic sum of basic columns by using some coefficients. And these are arbitrary coefficients just to make both sides equal, right? Alright, and I can do the same thing for the fifth column, right? Here all I need to do is just pick up the coefficients as 37 over 18, 61 over 18, and 13 over 6, and I can simply write the fifth column in terms of the basic columns. So this is a very important property, guys. So actually, for the time being, it may seem to be unimportant, but it is really important when we try to solve homogeneous systems, which is the topic of our next lecture. And in this lecture, actually I will use this very important property related to basic columns and non-basic columns, as well as I will be using the, of course, property of rank. Alright, and that's it for this lecture, guys, and see you in the next lecture, and until then, have fun.